So let us begin with so which one should we begin with? Yeah, so let us begin with one of the problems I had given to you, but we'll do a simpler version of that. Okay, so removing, so I'll just call this problem 1. Let me mention the topic, invariance principle. So as you can see, the handwriting is extremely bad because it's a very old laptop, so I cannot write well. Invariance principle, but I'll try. I have to also focus on thinking about the problem. So invariance principle. So problem 1. Let me name the problem: removing numbers from a heap. Yes, from a heap. So there is a heap of 10 numbers, a heap of 100 numbers. That exact number is not important. 100 numbers, and we are going to play a game. 2 players. We have 2 players, A and B, and obviously they move alternately. But let me write it. Moves alternate. At each step, can remove either 2 or 5. So the question I had sent, there was 2, 5, and 7, I think, something like that. Okay, or 2, 5, and 6, something like that. This one, we'll try to just do a simpler version first. Okay. 2 or 5 from the heap. I'm using these words heap because this can be used to generalize this kind of questions actually. And then the person who cannot make move loses. Okay, person who cannot move. So cannot move meaning when there is nothing left or when there's only one left, one number left. Cannot move, loses. So this is the nature of the game. And let's just say A starts. So I'll just say it in a more simpler language than I proceeded in the question. Can A ensure victory? So the idea is to discuss this. So I'm not going to say the solution because I don't know myself. Okay, but I know this can be done. And if someone knows the solution, try to help us with hints. Let's help each other to do this problem. Okay, even if you completely know it, that may happen. So does anyone have problems understanding the question? That's the first thing. Yes, Chandan, before you, I think you understand the question, but does anyone have problems in understanding the question? Okay. All right, Chandan, go on. Oh, 1, 4, and 7. See, 1, 4, and 7. You are suddenly saying, how do you know that? Like, tell us, like, take us through the thing, right? Otherwise, I don't think any one of us directly see 1, 4, and 7. I don't know. A will lose. So does everybody understand this notation? It's a very powerful notation, this one. Okay. So you can understand, like from A, I'm kind of taking this represents A is making the move, and -2 means he's removing 2 coins. And so 4, so with 4, A will lose. Okay, Adish, you were saying something? Uh-huh. Uh, okay, yes, okay. Okay. Right. So Adish, so Adish is saying that this is 4 is kind of like the end of the moves. We are ending up at 4. What? Always? No, no, no. No, no, that is wrong. It will not always work. So I mean, you can take some small numbers. Yeah, you may not believe, but you can take some small numbers and build on it, and A will always lose from there if B plays smartly enough. That is, no, no, but I am doing a simpler version of the question so that we can, because I don't know how to do that one. Okay, so let's do a simpler version first. So that is, I think, from some proper Olympiad, some hardware. Anyways, so yeah, so okay, but Adish, your idea is, so you think that it will not affect if it's a large enough number, then you can always make A choose freely, but I don't agree with that. So I'm not happy with what any one of you have said so far, and I myself don't know, but I know that we should take small cases. Let's take small cases and let's list down and try to see if we can say something. Yes. Uh-huh. Hmm. Okay, okay, okay. So you are saying something. Yeah, I understand, I understand. But let's still take small cases because this losing position, winning position, I don't know if everybody is comfortable with this. Okay. So let me put some, yeah. And you'll also get more comfortable, you will see as we do. So we'll see. Uh, so let me just say, let me make two columns here. Okay. In the left, I will write those, such that if A starts with that, then he wins, and those such that if A starts with that, then he loses if B plays smartly enough. I'm not calling them winning position, losing position, those complicated terms. I mean, I can just introduce them and try to do, but point is that let us just take small cases and see from which positions A is able to win. Simple as that. Let's not get into theory. So what about the number 1? If we start with the number 1, then does A win? If you start with the number 1, is A winning? Yeah, so this initial heap, okay, so if in this initial tray, it's not a heap, but if I put the number 1, then is A going to win? No? Yes, okay. So, so that, yes, we are always assuming that A starts. Yeah, so that's, yeah, okay. So can anybody explain? No, but if the beginning number is 1 instead of 100, so we are going to understand, yeah, what kind of numbers are going to make A win and so on, because we directly cannot jump to 100. Okay. Yes, right. So if you start with 1, if you start with the number 1 instead of 100, then A is certainly losing. Sorry, A is certainly losing. So it's this is in the losing. Losing means that no matter how smart he is, he will lose. Okay. So what about the number 2? Okay. He will win. Yeah, means he kind of has to win. It's not about some brains in this case, but yeah. What about the number 3? Win. Yeah. So if anybody says the answer, I'll write it. Okay. And if someone doesn't get it, you interrupt me. You just ask. Okay. Yeah. Because what about the number 4? So with the number 4, he is going to lose no matter what he does. Okay. So are the other people, Rasubro and Nagesh, are you getting this point about winning and losing? Okay, because we put some terminology from here. Okay, winning position, losing position, and then you can actually say it in terms of graphs, kernels of graphs, automata theory. All you can. Okay, so just getting comfortable with this is very good. 4. What about the number 5? No. If you start with the number 5, he will win if he removes the 5. If he starts with 5, but if he starts with 2, then he will lose. He might lose. Okay. So yes. Yeah. So I'm just saying that, like, yes. So I'm saying that in this case, it's based on the strategy. Okay. So you say that there are some kinds of games which are, I don't know what they are called. I just call them mindless games, where no matter what somebody does, the result, his outcome doesn't depend on their intelligence. But in some games, it depends, and so one can take advantage of that phenomenon. Okay. But in this case, if you start with 5, then A can win. So you guys will notice that A winning and B winning is not really the question. The question is, if I start with a number n, so if someone starts with a number n, then can they ensure victory from that number? Then we will call that number a winning position. Mm-hmm. Okay, so now I will use the word winning position. And so you see, I am not going to use the word winning for A or winning for B. Okay, I'm just saying if n is a winning position, and it's a very powerful language. Okay, like this. If n is a winning position, so it means that no matter who starts with this, if they play smartly, then they can win. They have a strategy to win. If n is winning, so yeah, Adish, what were you saying? Okay, why? Yeah, but n and n plus one is the wrong thing. N and n plus one, but something similar you could say. So would anybody like to say something along these lines? If n is winning, then Is it possible to say? Okay, what if I don't say this? What if I say n is a losing position? Because see, losing position. Okay, first of all, if I just write losing position, just answer what I'm asking here. Just because if n is a losing position, what does the sentence even mean? N is a losing position. Everybody clear? I'm not writing the definition. That's fine. Okay, losing position means no matter what he does, he loses. So we can comment a lot on the losing positions recursive behavior. Let's see. If n is a losing position, then can anybody say yes about n minus something is winning? मतलब कि n से जो भी whoever is starting with n, they are going to lose. What does this even mean? That is fine. Okay, no matter what, yeah, no, that is fine. But just in the one like recursively, what can you say? No, that is okay. But I'm just asking, what can you say? Like you made a statement about n and n plus one. In that sense, what can you say? Yes, that you can surely say, right? About the n minus one, I'm not sure, and I think that's not correct because then everything will be whatever. Okay, anyways. Okay. Uh, but you see, this is that does everybody agree with this? That if n is whatever Raghav just said, but if n is a winning position, n is a losing position, means that no matter what, anybody who, if it's A or B, that we have removed A or B from the picture in that sense. Okay, in that sense. Okay. So should anybody want to explain, except for Raghav, I think he says this. Can anybody explain why if n is winning, then n minus 2 has to be losing? Please try to explain. That is great. Okay. Would anybody else want to restate it in their own, in other ways? What Raghav said is correct. But please try to say it in your own words. That's very important. Because you guys have thought about these problems, but now you should try to say and check your thoughts. If n is losing, then why is n minus 2 winning? You can imagine A starting with, yes? Okay. Anyone else wants to say? Just what you said is not wrong. It's not okay. Basically, I have something in mind and I want to hear that. Yes. Yes. N minus 2 should be a winning position. Yes. Hello, am I audible? 3 and 5. No, but I am not. No, I'm not saying that. I'm saying that if n is a losing position, then n minus 2 is a winning position. No. If n is a losing position, then n minus 2 is a winning position. No, it makes a difference, right? The player who this thing. Yeah, that's the whole point, right? So everybody has said Nagesh play. Yes. Last time you were not less. So say it again. Nagesh, would you like to say if n is a position from which so suppose A is starting from n, okay, and we know that no matter what A is doing, he's going to lose. So then what can you say about n minus 2? Yeah, okay. So that's it's a new concept. So let me then say that all of you have kind of said it correctly. Some have said hard after. See what I'm trying to say. What does it mean to say that n is a winning position? Let's assume that A is starting from position n, and I am claiming that that n, sorry, losing position on this. I should focus on thinking rather than speaking too much. Yeah, sorry. What I'm thinking is that n is a losing. What I'm saying is n is a losing position. It means that no matter what n does from here, he's going to lose. What does it mean? It means that if n removes 2 coins or 2 numbers, he's going to lose. It means that from n he goes to n minus 2, and from here on he loses. He loses means what? He loses means B wins from this position. B wins from here. Sorry, I'm writing it twice because there's a part of screen which is damaged. I cannot see. B wins from here. We'll come to n minus 5 later. Just focus on this. Right? N loses, A loses from n means B wins from n minus 2. That's right. That's right. Okay. Yeah, because if you could not win from n minus 2, then it means that A will win from n, right? But A is losing. So it's just a simple, straightforward thing. You don't have to think contradiction proof. It's just simple thinking. Okay. Okay. Now this means that B wins from n minus 2 if he plays smartly. Okay. Which means that n minus 2 is a winning position. Whoever starts with n minus 2 is going to win. It doesn't B and A, that doesn't matter, right? Whoever starts from n minus 2 is going to win. So you see, that's what I'm saying. Is it clear now for everyone? Implies that n minus 2 is losing. And if I'm also maybe wrong, so you should tell me. Mm-hmm. No, no, no. But you see, why should it depend on, but that's what we are saying, right? If you're given the number n, if you're given the number, if you're given the number 100, let's say, and if you know that A starts from here and wins, okay, and if you're given the number 100, and if B starts, then won't B also win? So it depends on the number in that sense, right? If you're given the number 100 and A starts and he can win, let's say, then it means that if B starts from there, from that, then why not? If there is a strategy, we'll use that strategy, right? Well, at least we know that it will not depend on the person. Yes, so that's all. That's all. Now it may happen that from every position, every position is a winning position. That may happen, but that's not happening. We have already seen like 1 and 4 are losing positions. So it does depend on the number. In what? Yes, 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 yeah. So you're doubtful about that. That's why we have to do this problem. Yes, no, that's okay. That's okay. Yes, yes, yeah. So this particular observation doesn't remove that doubt. I understand. Sorry, yeah, that's wrong. Yeah, yeah. This particular one will not remove the doubt, but we'll see. You'll see. So vice versa is not true. That's why I'm not saying right. If n is winning, then the other is losing. That's not easy to say. That might be true. For some cases, it's not correct. Always remember that losing position gives you a lot of information. Okay? Don't remember, just try to think, right? If n is a losing position, it implies some very concrete thing that no matter what you do, you lose. So it means that wherever you go from there, n minus 2, n minus 5, in those using those rules, those are going to be winning position. That's what it means, right? Let's continue to take some more cases, then you will see. Yeah, this particular thing doesn't remove that doubt. It basically is saying that if you have losing positions, then you have winning positions also. You want to see something that will imply losing positions, right? Then you believe, right, that there are. So let's take the number 6. What about the number 6? Okay, okay. So A. So both sides. Okay, so that's fine. Yeah. The 6 is winning. Okay, what about the number 7? Okay, 7 he loses because he goes to, if he and you can see it in action. You can see our claim in action here. From 7, no matter what he does, he goes to those positions from where B can win. He goes to those positions from which are winning positions, which means he will lose. So it's impossible to win. Okay, no, that's fine, but it's a losing position. So losing position means that no matter what he does, so what does losing position mean? Okay, so 7 is losing position means that no matter what A does, if B plays smartly, then A will lose. That's the meaning of losing position, right? The other person is playing smartly. Otherwise, otherwise it doesn't make sense, right? Because both of us. So 7 is a, and so let's not get rushed to any conclusion. Just do it because this doesn't even take time, right? This very quick, this thing, right? And just keep doing it quickly. Now 8. I'm just writing 9. Now you can do it very quickly. Okay. So Adish, you see now the numbers are increasing. They've gone above 5, and still we are getting losing positions. Okay. 7 and 8. Yeah, but there will always be a pattern in these kind of games. We'll see that. We don't need to prove such things. Oh, okay. वो तो नहीं होगा ना, that cannot happen, otherwise everything will be losing. You see that, like just like said. 9 and 10 both are winning. Okay, that's a good reason. That's right. Basically, you should see. So one quick way to think, just a not quick alternate way to think would be that from 9, can A drive B into a losing position? Okay, that's the meaning of a winning position, right? N is a winning position means at least one of n minus 2 and n minus 5 is losing, right? Implies at least one. Okay, I'm not saying both. N is winning means that there is some way to win, right? So either n minus 2 is losing, or there's a contradiction there. So let me just. So does everybody understand this? N is winning means that A starting from, let's say A starting from N, B could also do. That's what we are using both ways to do these things so fast, right? Faster. N is winning position means that there is some way to win. It means that at least out of one of these two initial moves, there should be some further thing to win, right? So at least one of these moves should lead to a winning move, which means that, B is the person who's making this move from n minus 2 should lose. That's the same thing as starting from n wins. Or this is the way, that's what we are getting, some sort of an invariance, right? This n minus 2, this thing, this connections. Let's not really call it invariance and try to put a yes. So Nagesh, do you now see these two claims? Is to clear? Okay. Yeah. So it's a new kind of this thing, but it's very, and these are in general called game of name. Now all of you may not get the time to maybe search it and try to see. There's a huge theory of these games. Okay, combinatorial game theory. But those who have the time, you can. Yes, yes. In PSS is there, but it's a huge theory, combinatorial game theory. It's even a present active area of research. There are open questions in NIM, game of NIM, and so on, which I don't know anything about. I've just heard from far. N minus 2 and N minus 5. But I would be interested in. Yes. 12, 13 is winning. Okay. Yes, Chandan. Oh, you're taking mod 8. Yeah, so basically now to get a pattern, you have to take it modulo something. Now I'm not, let's say if I'm not smart enough to check mod 8, I would try to, let's say, check mod 3 first. Is there something consistent that you can say mod 3? So if you take these numbers, mod 3, what do you get? 2, 3 becomes 0, 5. Yeah, so that can also be done, but let's just, I mean, yeah, both ways is fine. The point is that now we know how to do this problem. This problem we cannot get out of hand. 6 will be 0, 9 is 0, and 10 is but then this is not good. So you see, mod 3 is not good because they're getting all the residues. So it's not going to distinguish. You see, if you do mod 3, no, I don't think it's a thing about after some time. You see, this is a very concrete recurrence kind of thing we are getting. So you understand, right? It's not like an initial thing. So you can, this way you can take mod other things. So some of you, tell me which mod should you take. So Chandan has said mod 8. So if you consider these numbers modulo 8, then let me just write them first and see. 2, 3, 1. Okay, 2, good. 4, 5. So 1. Okay, 14 and 15 both are two. So Chandan, you see, this is not good because you see, one is, I'm taking this is mod 8. Why I'm saying this is not good is because see, one is coming in winning also, and one is coming in losing also. If you take mod 8, the mod 8 pattern is not helping us to break the number system into winning and losing. So it's not good. But you guys can easily figure out some mod. Which mod? Let me write 14 and so Raghav, you say 14 and 15. Yes, that's absolutely correct because yeah, you can see. So think of what mod you should take. You can just think by patterns, or you can look at this and also think, and I'll also think. So I will want to take a certain mod so that it breaks up and gives us a concrete answer. Ye mod hoga, so it's winning. Then these mods means losing. But it's nothing very clever. You have to just take mod 7. Yeah, just take mod 3, 4, 5, 6, 7. 7 is the answer. So I'm not even going to maybe. I just write it. So I'm not going to tell you how theory and so on, because we can guess this very easily by just taking stuff. And usually your problems will not be some mod 57 or something like that. Okay. Yes. Yeah, you can. And actually, it won't take much time to actually reach 100. Right? Once you get going, it's just like writing numbers from 1 to 100, because you can understand like this 15, like just 16. So from 16, I'm a bit slow. Yeah, 16 is winning because from 16 you can go to 14, right? 17, 17 is winning, and then 18. So you guys can do it much faster. Okay. So mod 7, let's just write it. But then you see, we have to still prove it. 140 is winning, and what is losing? Sorry, yeah. Obviously. So you see, all the numbers so far are 140. Here, rest. Now, proof of this is just by induction. If you use these lemmas that we have, okay, just use the lemmas that you have and do it. You can, yes, but yeah, proof is very simple also. Yeah, but anyway, proof is important in that data generation. Good. Okay. If someone is having difficulty writing the proof, not now, tell me. Okay. I can discuss that. So wonderful, right? So now the actual question was uh, 2, 5, and 7 or 6. So now I'm not going to discuss this now. It can be done in the same way. I don't know what is going to be that number. So, but do that problem and tell me. 13. Uh, I don't know. I don't know why, but I don't think that it's just additive. Yes, but it is not. I don't think it is. I don't think it is additive like that. I don't know. Okay, you have to think, and I don't know the theory. Yeah, it's yeah. But try to write this, and this also you can see the pattern. And I do not know if there is a formula for these things. That if A, B, C are removed, then what modular you should check. I do not know if there is a formula, and if there will be, it's probably going to be. I just remember some theory. There's some base change, and this way. But I don't even know if that gives a formula. Okay, because there are 3 numbers, so I don't know. 100 is a okay. That we should answer the question. 100 is a winning position for this for our original problem for the question that we are doing now. Yes, that is a question. Okay, but you have a lot of tasks to do. You have to complete the proof. If you don't write it, then you have not done the problem. You have to try to write this. So you can just pick like n is 2 mod 7 is winning. You assume the smaller cases, and then you try to drive it to a losing position. Okay, try to write it. Okay. So now, in yes, and I do not know the intuition why, but we have a very strict recurrence. Hmm? Yes, yeah, or he should know that there is a modular arithmetic pattern. Then he can always be on the lookout for that. Yeah, but 2 and 5 and 7. Yes, yeah, that's right. You should do for large numbers at least. And, and no, but there is a it can also be framed in a certain way by partitions and so on, I suppose. But let's move to the next question. Some time. So that was the goal for us to solve this problem. Okay, means together. Otherwise, so that now when you meet, there are several versions of this. Okay, there could be 2 heaps. Okay, you could have 2 heaps, and then you could remove some simple like 1 or 2 numbers, something like that. Usually, it will not be very complicated. If there are 2 heaps, and maybe they'll have 1 number to remove or 2 numbers, something. And there are also similar techniques work. Uh, okay, similar techniques work. There will be a modular arithmetic pattern in what I have seen. Okay, and all the problems I've seen, it's usually like that. But, let's now go to many problems. Which one? No, I've not even read that question. That is there. Let me then do this one. I don't know. On table there are 100 coins. Oh no, this one is just what we discussed, right? Yeah, this was the only question I had seen. Okay, I had seen this one also. Let's see. This I had not sent you guys. Okay, so there is a white black, and see, because this is similar, that's why I'm doing this. Okay, because we just want to see if you can, if you have learned. So it's not similar actually. And so this is not a game, it's an invariance problem. Okay. At each step, choose two distinct colors. Choose two distinct colors. Remove one chip each of each color. Remove one chip each of those two colors, and add. Oh no, let me just do this one first. Just remove one chip each of those two colors, and yeah, let me do a simpler version. Okay, again, I just want to always do simpler versions. Okay, of those, and I think this will be simpler. And add one, add one chip of the third color. For what, and this is a simpler version again, for what n, what n, the n here, for what ABC, starting ABC, can we end with one, can we end with one chip? Yeah, that's the question. I think this question makes sense. Let's try it. So yes, this is a different question. So I've changed the question because this is easier, I think. No, just any color. You just want to end up with one chip. Yeah. Let me do an example. So suppose you're starting with 5, 4, and 3. Okay, so this is white, this is black, and this is red. So what is the move? We are going to choose two colors. Let's say I choose black, white, and black. And I am removing one chip each of those two colors. I'm sorry, just 1 second. I should close this right. I'm going to remove one chip of those two colors which I've chosen. And I'm going to add only one chip. So I've removed two chips. I'm going to add one chip of the third color. So you see, my number of chips has gone down, decreasing by 1. See, there is no guarantee, right? Because eventually, no, but just imagine, if you ended up with something like two white chips, because you may not be able to make a move, right? You have to choose two distinct colors, right? So you may end up with I need to have two colors to make the move. Okay. So the main observation, one good observation that Rasuda has made, I mean, yeah, number of chips is going down. So, but still, you see, you may just end up with one chip. That's why that was my goal in this question. That question I found a little tricky. I'm not able to do it. This question, let's see. This question I think is easier. Just think. Let me not speak anything for 2 minutes. Just think. Okay? And if you have questions, then you ask. Say something. No, not always. No, not yeah. So I should mention that for what a comma b comma c can be end. So I didn't say always. Yes, can be end. So for what a comma b comma c is it possible to end with one check? I mean, so I'm basically asking for what a comma b comma c is it not possible? For what for what a comma b comma c is it? I think this is an easier question to answer. Okay, is it not possible? Because invariance principle always is easily tells you what is not possible, right? You start from somewhere, you make some moves, you show that those moves don't really change some feature, and so where you end up will have certain features, and so it tells you where you cannot end up, right? Really basically, because you could end up with other places also, right? But I mean, no. So let me just say this point again. I think all of us should just we can benefit from this. Is just the whole because like just apart from this question, like, how would you know that this is an invariance principle type problem or okay? The point is that like let's say that A is a some situation from which you're starting, and they're asking you to show that you cannot reach B. B is some other situation. Okay, now this A and B is not this A and B. So it's a state, and this is some state. Okay. Starting with a state A, no, it could be some configuration of a chessboard, it could be something. Starting with a state A and there's a state B, which exists. But the question is, or let's say they ask you or you feel that it's not possible to reach from state A to state B by certain moves. Not possible to reach. Their invariance principle can help you. Why? Because invariance principle will, because let's say, first let me just moves. So you make these moves. And most often these moves are reversible, then a lot of theory groups and so on come in the picture. But just some moves, right? In some other states, and again we make moves. and let's say you're told to say that you cannot reach B. There invariance principle helps you, because invariance principle will tell you that something, or no, finding invariance, finding some invariant, meaning finding something that does not change when you change these moves. Okay, it could be a quadratic equation and that parabola, and you kind of rotate it or something. The discriminant doesn't change. You translate it, the discriminant doesn't change for a quadratic, right? It could be in many things. Or you take a determinant, you conjugate it from both sides. Take a matrix A, P inverse AP. The determinant is invariant, it does not change. I mean, those are the actual places where it's mathematical use. In CS, it's used the way the questions we are doing. Okay. But we make these moves and we try to ask, okay, what does not change? We find something that does not change. Once you find something that does not change, it means that all the places you reach will have some feature in common with A. Okay. Now B does not have that feature, then you are sure to say that you cannot reach B. Okay. But if the question is to show that you can reach B, their invariance principle does not help you, at least in a straightforward way, right? If you want to show that you can reach B, their invariance principle does not help you. Because you see, right, invariance principle is like finding an invariant. Because invariance principle will tell you that wherever you reach, it will have that feature that A had. But it is not saying that anything that has that feature that A has can be reached. Right? When you're finding an invariant, then it means that wherever you reach, that will have that feature in common with A. Okay. But it doesn't mean that anything that has that feature can be reached. Well, in a lot of times you can predict that with some theory and you can prove it later. But that is the difference. Okay. So there you have to use induction, you have to use some strategy, like you have to use some constructive so that you can. Okay. So most often both have to be used. This can be said in very interesting language of orbits and so on. This is just let's think about this question. If you want to ask something based on what I've said, you can ask. Otherwise, you can think of anything. Just yeah. If we are going back, if you want to have this, or you see this or this, then the set. Very good. That's, I think, right. It actually, okay, anyways, yeah, let's see. Conceptually, it doesn't matter. Yeah. You can write the other cases similarly, yes. It should be this. That's the only possibility. Like ये 0 हो गया, मतलब कि it was 1. And but yeah, it could have two possibilities, I think, right? It could be that it was like this, or just symmetrically. No, 1 comma 2 comma 0. Already you guys can try to see if there is something common in all these numbers. Which one? What is that? Okay, so you're saying that odd. So you're saying if A is odd, then B comma C has to be even. Okay, you're not saying. If A is odd and B comma C are even. Okay. Okay. Oh no, sorry, I'll return. Yeah. Mhm. Right. That's right. Mhm. Sorry, A. Sorry, say again. That comes down, yeah, but that is, yeah, that is not useful in that sense. Okay. Uh-huh. Certainly, certainly, yeah. So yeah, that's right. I think that is exactly the point, right? Yeah. So basically, see, it's very simple. Like I think from what Rasubra said, also we can extrapolate in this simple language. We can say it in the basically see if let's just imagine, right? I mean, if you start with three events, okay, then you'll end up with three odds in the next step, right? And then you'll again end up with three events. Will you ever get 100 or anything like that? No, it's impossible. Okay, I mean, I will try to use Chandan's language if I need it. Yeah, maybe in other more in other cases I will need that. But this is clear. Okay, that I cannot don't want to start with three events or three odd. These are impossible. From here, it's impossible. That's everybody can see that because each move, the parity of each of them is switching. Okay, so yeah, something like what Chandan said, the difference and so on. Let's keep this. I mean, let's just take other combinations, right? What else is there in this question now? Let's take other combinations. Yeah, all of what I realize is that all of us need more practice of combinatory specials, I mean, me included. Yeah. So there is this odd, and let's say if you start with this is the other possibility, right? So from this possibility, is it possible? Does it look that it is possible? If you start with one odd and two evens, so as Chandan has said, this difference, okay, A minus B, this difference, and B minus C and C minus A, these three differences, modulo 2 will remain constant. I'm not going to use it, but we can observe it if you want. I'm going to use it, but in say it in a simple way. Just the numbers that are next to each other and cyclically also. But am I wrong? Yeah, this is correct. Because that's what it means, right? That the parity is changing of all of them. So the difference in parity for every pair is not changing. That's the same thing. Right? So from here, it certainly looks like it is possible. Is that, am I right? Yes. So point is that like it's like here it's, you can see it. You see, the parity of each number is changing. Parity of each. That will not change. Right? Parity of each number is changing means what? That the difference in the pairs. If you take any two pair, you take any two in these three numbers, or even if you had four numbers, right? You take any two of them, because both are changing, right? Right. And even if you had like A, B, C, D, E, right? If this was changing to A plus 1 or A minus 1, it doesn't matter, right? And if the D was changing to D minus 1, you see, it's a general comment. So it's the same thing as saying that the parity of each number. Mod, yeah. Then you see. Bracket. Yeah, that I the kind of. So from here it looks possible. You see, I think so, right? Like it looks possible that from, if you start with odd, even, then it looks possible that you can reach 100. Right? I mean, our invariance is not contradicting this. Our invariance principle is not contradicting it. Right? And similarly, if you basically, no, as I said, it will never infer, it will never, it will never constructively tell you. Invariance principle, that's the nature that I explained, right? So now you have to find out a direct way to prove that it is possible. So the guess is now that it is possible, because now what you can do, the rest of the strategy of the question should be that you take some numbers like this, okay, in which there is one odd and two even, or two odd and one even, same thing, right? And you try to get to 100. Okay, then you will find a way to get to 100 or 010. Do you guys get my point? Right? That you try to start with some number, like you start with 5, 6, 2, and try to get to 100. Okay, and then maybe you could use some sort of an induction. Think induction is again the answer, right? Because you'll again end up with a similar kind of tuple, similar kind of triple, a triple which has similar properties but of a smaller size in some sense. You can use induction. Yeah, and for that we have used the invariance argument. Obviously, in the end of the day, to do any rigorous proof, it's induction. That's I agree with you. But the key is the invariance, right? That is those are eliminated. Yes. 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 So let's actually try to do this OEE, or let's not do it. Leave it for you guys to try, because I have to finish my dinner today. Okay, but induction is the key, because you see, you can assume. So let me actually write a bit so that you guys will know I'm not just telling you something wrong. You would know it either ways, but my point is that you assume that for all, I mean, for 102, and though you can prove for all a plus b plus c equal to k, if two odd, or if all three parities occur, one even, or we are assuming something strong. If you want to use induction, always assume something strong, sometimes even stronger than what you need to prove. Okay, if you feel it's correct, assume it, and the induction, it's helped in that way, right? Two even, one odd. But this we know it should be true. So we are assuming that for all numbers, not just k, I'll say all numbers less than k. Okay, so it's like for all numbers for which the sum is less than k, if the triple is of this kind, for which we want to prove the answer is yes, you can reach 1, 0, you say that, you assume, yeah, for all numbers a plus b plus c less than k, if this is this, then 1, 0, 0, or you see my point, right? 0, 1, 0, or I have to say all this can be reached, can be reached. Okay, but then then it's simple, right? Because now if you have a plus, now if you have some other numbers, right? A, C that you're starting with, and they add up to k. Now you want to prove for the larger case. So you see you make this move, and the triple will again fall into one of those categories. Am I right? It will fall, right? It has to fall. I mean, you don't have to be smart here in the sense that you can make any move. Okay, and you can assume that A is odd or whatever, right? So you can assume that C, let's assume that C is even, because you can assume it like this. And then you guys know very well. This is again a triple, and it is again of that form in our assumption, right? It is even, odd. It is in our assumption, and also this sum is k minus 1 less than k, right? These three numbers again add up to less than k, so I can apply my induction, and I'm done. See, induction is so nice. Less than k, and also yes, certainly. Okay, does everybody understand the idea of this? Okay. You can also ask me later, but fine. Okay. Yes, Rasura, please. That's the whole point. Yes. Uh-huh. Mm-hmm. Okay. Is also winning. Yeah, so in this case, winning position is invariant. Right? It doesn't change in that sense. It's also winning. Okay. Is also winning. Yeah. Mm-hmm. Is also winning. Uh-huh. Why? Yes, that's what we have already. Okay, so you're using that. Okay, yeah. Okay. Okay, so A is odd because that has to be true. Otherwise, there's no way to win. Okay, B is odd and C is even. Okay. Okay, but you can say in this way, but that way is same. Uh, uh, 1 comma 1 comma 0 is winning. Yeah. Hmm. Okay. No, but A comma B comma C may be very different, right? Maybe 100, 100. Okay, right. So it's a you can reach. Yeah, got it. So you have actually given an algorithm, right? You have given an it's a construction. Yeah, he has given an algorithm with which you can actually reach. That's very fantastic. This is the last step, yeah, but he's saying that if you start with this, then he's telling you how to reach A comma B comma C. Mm. Yes, yeah, that's right. That is right. Mm-hmm. Yes, from no, not all of them, because he has made an assumption here. No, half, one third, like odd, even, hai na? So all of them I don't think can reach. Like 2 odds and 1 something. Yeah, but you can see, you can work that other case out. Yeah. The point is that he is actually giving some sort of an algorithm, right? That if you do the reverse, he can actually tell you the path. Okay. And the path is like, as he has said, that if it is like a 5, if it is like 5 comma 2 comma 2, then he has explained how to go from here to here. Can you, Rasubro, can you say again in this specific case? That, okay, yeah, that's right. 1 comma 0 comma 0. And so tell me how you'll go to 5 comma 2 comma 2. Tell us, or you can go to 3 comma 2 comma. Yeah, so he's basically he's using this thing, right? That you can add 2 with everything. This is the key thing, I suppose. And now you guys can build it, right? It's just puzzle. Yeah. Simply this step. Okay, wonderful. So that's well, it's the same. So induction will also can. Yeah, all 3 parities. Hmm. Hmm. Counting the number of paths can also be a problem. Yes, certainly. I think what will be true is the parity of the number of moves needed. That will not, that will be invariant again. You can try that. Okay. I feel that is true. Like number of moves needed will not be same, and as you've already said, there will be different paths also, different number of paths. Like you can be stupid and go round and round, right? Or no, sorry. Yeah. No. So forget what I said. Yeah, no. The length of the path will be fixed. What you said is an interesting question. How many paths? Yeah. Length of the path cannot be changed, right? Because at each step you are removing one. So it will always be, it's like a tree, it's like a branch, but the height will be same for each, right? But yeah, the number of paths, I think it can be done because we have a recurrence here, but let's not go into that now at least. It's a good question. I will think about it definitely. Yeah. I'm interested in these kind of questions. Okay then, so I'm stopping here. Okay, if you have any doubts, you can ask me. Nagesh, you can tell me how you like the class and so on later in the mail, or you can also call me and so on and tell me. Okay, then we can see.